neural networks and kind of make a composite function out of those two, found functions, and be able to treat that composite function as a single classifier for the two neural nets?
Yeah, that's a very important point and a very good question, I think. So we do that, we call that like network ensembling. And the way we train these networks, there is a lot of randomness and stochasticity involved. And what happens is, like, if you train like similar networks multiple times, you might get different kind of functions. So that's called network ensembling.
Okay.
So
cool.
that's used in machine learning. Yeah. All right. So if there is no other question, we can continue. So this lecture is about convolutional neural networks. And let me give you like a very interesting quote just to cheer you up. And this is about deep learning. So if you go out in the society and you say that, okay, you work in deep learning, you're a deep learning expert. So the society will think like you do something like this because they are like motivated by watching movies, right? And when you will ask your friends, then they will think like you're doing something like this because they are well educated and they might be like engineers, so they know like how chip works, how human brain works. So that's really interesting. And the other computer scientists, because they are not paid that well, so they think that we just are lying like on a pile of money. And that's actually true these days, because if you're doing deep learning, you're going to get like a very well pay even after like just after graduation. So that's true. So that's like another motivating factor for you. And this is kind of disturbing. Like if you talk to a mathematician, then their perception is like we are doing nothing. And there's a reason for that. The reason is like whatever we are doing these days during deep learning, we don't have a well theoretical grounding for that. But of course, that's an evolving area, so researchers are working in that direction as well. But this is like the current state of art. And this is like a very famous scientist. All of you might know this, Jan LeCun. He's a like chief principal scientist in machine in Facebook, and also like a faculty at NYU. But this is like exactly what we do, and you will see like in most of your assignments which are related to deep learning, you just use existing code. So there are deep learning libraries out there. You just reuse them and try to solve your problem. Okay, so that's a relief. And something more to motivate you further. So let's try to go through like some simple examples which shows what deep learning can actually do, or rather like what CNNs can actually do. And by the way, I mean, there are other kind of networks out these days which are called transformers. Just in case you're interested, they work a little differently as compared to CNNs. Their root lies in natural language processing, the natural language, right, the text. So their functioning is a bit different, but they are like showing very promising results in image domain as well. But it's fine, still we have CNNs. So it can be a competitor, but CNN is still required. So if we have this video, and if we want to estimate depth out of this video, right? So depth is like, as I discussed, it's how far each pixel in this video frame is from the camera. Then there was a recent method in 2019 using CNNs. This is like what we can achieve, which is quite impressive. And here you can see that each pixel in this map is showing the depth of that location. And you can see the algorithm is doing pretty good job here. And of course, this is like using video, so we have some help because we have that motion. And again, doing this just using images is quite very challenging, not that trivial. But this, again, these results are very impressive. So once we have this depth information, we can do a lot of things, right? For example, you can have this like stereo view, right? Because you have the depth and you have seen the scene like while your frames are changing. So you can have the stereo effect, again, which is very cool. And the another like a very interesting area is super resolution. And the idea here is, what if we have very low quality images? Can we generate high quality images using them? And on the left, I'm showing like the input which was given to the network. So you can see like it's very, very blurred image. And on the right is the output of the network, which is high quality image synthesized just using the deep network. And you can see like this is quite impressive. And this is pretty recent, I think last month. So the images on the right, like you can see it's changing. So that's kind of as the network is training, so it's getting better. So initially it's just outputting garbage values, right? Just random values. But over time, you can see that it's improving. Okay, so that was just another motivation. And there are pretty cool things which you can do using deep learning. Now let's try to understand like the basics of CNNs, how they work, and what can be done using these CNNs. So these are again just a class of neural network. And the way it works is we take images as input mostly, but again, we can have other kind of inputs as well. We'll see that later. And then what CNN will do is they will make some kind of prediction about these images. So earlier we saw like they can do super resolution. So for each pixel, they will generate a very high quality pixel, or they can predict depth. And this is a very general architecture of a CNN. So whatever CNN architecture you generate, it will have similar kind of architecture. You will have some input. It could be image, it could be video, it could be anything else. And then you will have these layers, subsequent layers. So neural networks, you have like layers of neurons. In this case, we'll have layers of convolutions. Right? And these convolution operations will give you feature maps. And these feature maps are something which you're extracting from your input data. So again, you will have like maybe subsampling layers. We'll talk about that later. Again, you will have convolutions. So this is like similar to neural network. You have these layers of different convolutions and some other operations. And the idea here is like extract some meaningful features from the input image and refine them over time. And at the end, you get like some feature set, which you say, okay, represent your image. And then at the end, you use this fully connected layer. This is again a neural network, which we just studied in the last lecture. And that's going to give you the output. And sometimes you may not need this fully connected layer. Sometimes you may need, okay? So that's a variation. But this is like a general architecture, which you will see like in almost all the networks you develop. So talking about this, again, this CNN, this is not something new. And I think there's a question from Fernando. Yeah, I think we'll cover this at the end of the lecture. This is just out of context. Just remind me, Fernando, in case I missed this. So question from Connor, will you always need fully connected layer for the fan classification? Yeah, that's what I said. I mean, you may use it or you may not need it. We are going to talk about that as well. In what cases you will need that and in what cases you can avoid it. Okay, so you might not need it always. So as I was saying, this is not something new. In like late 1990s, LANet architecture was proposed, and it has structure something like almost similar to what I just described. Input image, your convolution operations, then fully connected, and finally your output, right? So in this case, the only difference is you can see the resolution of the input image. It's pretty small, 32 cross 32, and it's a grayscale image. And these days we don't work on like such small resolution or like a grayscale image. I mean, in most of the cases, we try to use the RGB image if it's available. And again, the resolution, it depends like what problem we are solving, but mostly we work on high resolutions. And that's due to like the GPU resources we have. So Alexnet 2012, this was like the first breakthrough in deep learning. And this is like when it all began, and it's still booming after like 9 years. But this was the first work. And again, the architecture which was used in this work, it wasn't new. It was the same LANet architecture which I just showed you in the previous slide from late 1990s. Okay. The reason why it was so successful was the availability of large amount of data. And the second reason was the availability of resources, which can be used to train this network using that large scale data. Okay, those were the only two things. The technique or the science behind it, it wasn't new. But still, with those two things, you can see here that the error rate on this data set, I think we have talked about this data set. This is ImageNet data set. So the error rate was dropped to 15%. And this was a huge improvement over like the second best entry, which was at 26. And prior to this, like the progress was like maybe 1 point, 2 points, or 3 points. So if you look at that, like it's 10 to 15 points jump. So it was a big deal. And that was the architecture which was used. And you can see that it's almost similar to what I described earlier. We are going to go through this in detail in the later section of this lecture. Okay, and as I said, it started in 2012, but today we are using CNNs like in almost all the problems. So classification, object detection, semantic segmentation, it could be captioning. So in captioning, even like text is involved, right? Even then we are using CNNs. We can have other problems, style transfer. So most of these problems we have covered like in the introductory lecture. So I'm not going into detail because you should know like what each of these problems are by now. Okay. So the other important point here is CNNs are not useful just for images. We can use CNNs in natural language processing as well. So the idea here is what we can do is we can use for text classification. And what we do is we can actually try to convert the words into vectors. So if we have these a sequence of words, we can convert each word into a vector. And once we have this vector for a sentence, we can create this matrix. And once we have this matrix, we can just pass this to a CNN because CNN takes like a two-dimensional space. Okay. It can be used for audio research, for speech recognition. So what we do here is we can represent like these audio signals in the form of spectrograms. So that looks like a visual data. So that's fine. So it's all about if you can convert your data into a matrix format. And right now I'm just saying 2D matrix, but it doesn't have to be 2D matrix. It can be just a one-dimensional matrix, just a single row, right? Or it can be a three-dimensional matrix. So 1D convolution, right? So audio, you don't have to always convert this to spectrograms, although it works better when you do that. But essentially, you can just take the audio signal, which is a one-dimensional signal, and just use 1D convolutions. You can have high-dimensional data like 3D like videos, where you can use 3D convolutions. And of course, you can have four-dimensional data, which could be like space and time. Then you will need 4D convolutions. So it's all about like representing the representation of your data. And as long as you can represent that as a matrix, you can use CNNs. Okay, so let's now try to go through like the background which we'll need to understand these CNNs and what we already know. So we know that what's the general architecture of a CNN. We have seen that earlier. So we have this input, and again, this input could be image, it could be video, it could be like a spectrogram, but it should be some kind of matrix. Okay, so that's the first thing. So if it's an image, then you know that you can represent image as a matrix. If it's a grayscale, you will just have one channel, but if it's a RGB image, you will have 3 different channels. So that's a 3D data, but again, you can use matrix for that. The second stage is this network itself. All right, so this network will take this image as input and then try to extract features in subsequent layers. And we are going to dissect this like very carefully how exactly the network does that and extract some kind of features. So this is the like the main thrust of CNNs. So these are the concepts which we will need like to understand that part. So we'll need image filtering. So we can do a quick recap of image filtering. So probably, okay, let me do this because if we do a recap, I'm sure we don't have enough time. So then we'll have to do this recap again. And so what I will do is in the next lecture, I will quickly go over this. Probably you can try to revise these concepts before coming to the lecture. All right, so we'll quickly go over correlation, convolution, filtering, edge detection, then MLP we just covered, so that's good. And the learning phase. So we'll start from here, quickly going over like the previous slides. And I think we can stop it here today. If you have any questions, please let me know. I think there was a question which I didn't answer earlier. Okay, so the question was from Fernando. For programming assignment 1, would you like the Canny source code in a specific way? Or can we submit a notebook containing the code and some outputs? Yeah, ideally, I think you should submit the code, just the code, not the notebook. Right? I mean, even if you are working on a notebook, I mean, that's perfectly fine, but you can just export that code, right? So just do the export and submit the code. And there should be comments on your code. And if you're writing comments on your notebook, and if you don't know like a trivial way to export those comments as well, but ideally you should be able to do that, then I think submitting notebook is also fine. And of course, there will be no negative marking if you submit a notebook. Okay. So Fernando, does that answer your question? Okay, all right. So any other question we have?
Yes, I have a quick question, Professor.
Yes, go ahead.
You talked about transformers and CNNs, and the recent examples I guess you probably showed were for the CNNs, like the recent works that you just shared. And lately, there's been a lot of hype about transformers, in particularly natural language processing. So, like, is there something in the search domain going on, like transformers are ending up replacing the CNNs, or is it the other way around?
So not replacing, but what I'm seeing, like based on what I've seen, like some recent papers last month. So it's kind of combination of both. And probably I think the lecture has ended, so I can talk a bit more about that. So transformers mean they have the intuition in natural language, right? And there the idea is to make use of a context.
Mm-hmm.
So the way they work is, for example, let's say if you have a long sentence, and let's say you want to make some inference about the sentence. So if you want to make inference about like any time step in that sentence, then can you make use of the full sentence itself? So that's the bigger context, right? So that was pretty hard.
Right.
But transformers, it actually can capture the full context. It doesn't matter how longer your sequence is, very effectively and efficiently. And that's why it's giving very, very good performance. So that's
Using it.
kind of, yeah, so that's the intuition, like transformers can capture long range dependencies. Okay. But CNNs, I think we will cover in the next lecture, but I mean, I have covered like filtering and all, right? So filtering, when you do filtering, you're kind of learning local correlations. And essentially, if you go deeper into a network, you do learn longer dependencies as well, because your receptive field will grow. And again, if you don't know what receptive field is, don't worry, we're going to cover that in the next lecture. But again, that connection is pretty weak in terms of like long range dependencies. So I think the way I see it is CNNs are good to learn local correlations, and transformers are good at learning longer correlations, even in your image, right? It doesn't have to be just your sentence. It could be your video, it could be your image. So if it's a video, if it's a very long video, then you still need the long-term dependency, right? Which is
Right.
hard to learn using CNN. So
Okay.
the integration of these two, I think, is where the field should go. And that's like something which we are trying as well. But again, it's still like
Is
ongoing
it
research.
something similar to vision transformers?
So vision transformer, they don't use CNNs, right? They are purely based on transformer.
Image, yeah, they're image patches that they're using.
Right. They're not using CNNs.
Okay. So the work that you guys are trying, is it like inducing attention mechanism into CNNs to make it be able to capture long range dependencies?
Yeah, that's one way to look at it. But the other way could be, I mean, if you think about this at a conceptual level, as I said, transformers, they are good at learning long-term dependencies, right? And CNNs are good at learning local dependencies. So to exploit that property, I mean, it could be attention, it could be any other way.
Right. Oh, right. That's amazing. Thank you.
Okay, so any other question before we end today? So yeah, if you can do attend the tutorial on Thursday, I think that will be really, really helpful for you to complete your programming assignment. And I will encourage you, I mean, if you don't have a very strong background in Python or programming, you should definitely attend that, because I think very, very trivial questions will be answered. You can ask whatever you want. Okay, so that will be, I think, a really great help for you guys. Okay, so if there is no other question, let's end it here today. Right, I will see you in the next lecture. Bye.